Hello everyone, my name is Fernando Monteiro and I am here to present the study entitled The Role of Background Color in Pollen Recognition Task using Convolutional Neural Network. The motivation for this study were the importance of identifying and counting pollen and the difficulty in being able to perform these tasks manually. These tasks are important in pollination, crime scene investigation, allergology, as well as botanical and geographical studies concerning origins of honey to prevent honey labeling fraud. Automatic pollen counting and classification can alleviate the problems of manual categorization such as subjectivity, differences that are frequently imperceptible among pollen grains, and time constraints. Visual classification performed by humans operators is a hard and time-consuming task with a performance that is reported to be around 67%. This is due to the human difficulty to remember all the features related with a large number of pollen types. My presentation will start by talking about the research problem, followed by an overview of related works published in the last years. Then I will present the proposed approach and the implementation issues. After that, I will show some results and analysis and terminate with the conclusion and some future work. The acquisitions of images usually has some different sources, resulting in images with different background, as shown in figure. We observed that existing published convolutional neural network approaches to pollen recognition use the foreground and background information in the training process. In those approaches, background and foreground pixels contribute with same influence into the learning algorithms. However, as each pollen type has a different background from the other types, we want to verify if the CNN may be biased by capture relevance from background. Our work focuses on identifying and counting pollen grains and studying the influence of background when using convolutional neural networks. To do that, we use the DenseNet 201, that is a state-of-the-art CNN. We found that previous related works used usually support vector machines or neural networks to solve this problem. In all those works, the combination is the small number of pollen types used. More recently, Sevillano et al. In their works of 2018 and 2020, used a large number of pollen types, 23 and 46, achieving accuracies of 95 and almost 98%. Astolfi et al. In 2020 presented a new dataset with 73 pollen types and made an extensive study with several CNNs that served as basis for our work, achieving an accuracy of almost 96%. In this study, we used the same publicly available dataset as in Astolfi et al. The Pollen 73 is an annotated image dataset, publicly available, for the Brazilian savanna. It contains pollen grains images taken with a digital microscope at different angles, composed of more than 2,500 images from 73 different pollen types, containing 35 samples for each pollen, except in 3 of them. From the results presented in Astolfi et al., we observed that this small number of samples biased the recognition, resulting in the worst classification scores relative to the other pollens. And to overcome this problem, in our study, several images were generated through rotating and scaling the original images, ensuring the same number of samples for each pollen type. Although the image have different dimensions, they were resizing according with the image size of the CNN input. As we can see, there are some pollens very similar with the others, increasing the difficulty to obtain a correct classification. We construct a new dataset by segmenting foreground information, allowing the independence of training and testing process from the background of each pollen type. This segmentation is done by thresholding techniques and mathematical morphology. We choose a popular CNN architecture, the DenseNet 201, due to its performance on previous classification tasks. DenseNet model is built by dense blocks and pooling operations, where each dense block is an iterative concatenation from all previous layers. Within those blocks, the layers are densely connected together. Each layer gets the inputs from all preceding layers and passes on its own feature maps to all subsequent layers. A CNN model can be thought as a combination of two components, feature extraction part and the classification part, and thinking that convolution layers are the main strength of a CNN model, and automatically detecting meaningful features, given only an image and a label, is not an easy task. The convolution layers learn such complex features by building on top of each other. The first layers detect edges. The next layers combine them to detect shapes. To following layers merge this information to infer that it is a pollen grain. To be clear, the CNN does not know what a pollen grain is, and by seeing a lot of them in images, it learns to detect that as a feature. The fully connected layers learn how to use these features produced by convolutions in order to correctly classify the images. Usually, constraints of practical problems, such as the limit size of training data, refrain the performance of deep CNNs trained from scratch. So, to overcome this problem, we use the transfer learning technique. For the experimental setup, the CNN batch size was configured to 12, and they were trained with 30 epochs. During training, all images go through a heavy data augmentation, which includes horizontal and vertical flipping, complete random rotation, rescaling factor between 70% and 130%, and horizontal and vertical translations. We adopt a five-fold cross-validation on dataset, where each fold the dataset was split on 70% for training and 30% for validation. This second dataset for validation was not seen by the network during training. This allows that the CNN model be iteratively trained and tested on different sets. All CNNs were trained using the MATCOM.NET MATLAB toolbox. in a virtual machine with a pair of NVIDIA RTX 28. To evaluate the influence of pollen background, we use a cross-evaluation approach. First, we train the CNN with original images and tested it with the original and segmented. Secondly, the CNN was trained with segmented images and tested with segmented and original images. CNN used in this study has good performance as it allows us to conclude that segmenting pollen grains image improved classification performance, achieving an accuracy of 97.4%. The DenseNet classified correctly all the images for 65 pollen types, and for the other 8 types it misclassified up to 2 images per type, with a total of 11 false positives in these 730 tested images. Here we have some false positive results, and as we can see, although similar, they have the same background information. The network trained and tested using the segmented images produced false positive results that are misclassified as pollens that have high similarity with tested one without the influence of background. The lowest accuracy result was achieved with the pollen types Dipteryx alata and Mircea guineensis. These pollen types have predominantly rounded shapes and high texture that are normally learned in first CNN layers. Since the transfer learning process changes only a set of the last CNN layers, it does not change those learned features during the training process with our own images, producing some misclassified results. In this table, we compared our results with other previous related works. The accuracy rates achieved by the DenseNet network are relevant due to the amount of pollen types used in the Pollen 73 dataset. Since Sevillano et Elias obtained a high accuracy, however, they used the dataset containing only 46 pollen types. As conclusion, to promote research in the automation of pollen classification, we report performance for pre-trained CNN topology applied with a different dataset. Using a sufficiently trained deep learning model, we are able to recognize pollen grains from 73 pollen types, one of the largest number of pollen types studied until now, achieving an accuracy of 97.4%. In the future, we plan to combine different CNNs to further improve the performance of the automatic system. Here we have some of the most important references in the area. And if you want to keep in touch, these are our contacts. I hope you have enjoyed our presentation, and thank you all.